From the Library of Congress in Washington, D.C.
I'm Jennifer Harpster, a reference and research specialist here at the Library of Congress with the Science, Technology, and Business Division. I'd like to welcome you to today's program, The Fantastic Voyage of MMS, Understanding Magnetic Storms Throughout the Universe. This program is part of the 2015 series of lectures that are presented through a partnership with our division and NASA's Goddard Space Flight Center. And I'd also like to report that this is our 9th year that we've been partnering with Goddard, and we look forward to many more years. So this past March, NASA launched 4 spacecraft for the Magnetospheric Multiscale mission, or MMS. MMS is the first mission that is dedicated to studying the mystery of how magnetic fields around the Earth connect and disconnect, explosively releasing energy via a process known as magnetic reconnection. MMS will observe reconnection directly into Earth's protective magnetic space environment, also called the magnetosphere. And reconnection is a common process in our universe and one of the most important drivers of space weather events. It is my great pleasure to introduce today's speaker, Dr. John C. Dorelli. He's a space scientist and a computational physicist at Goddard. He is also an instrument scientist for the Fast Plasma Investigation Instrument that's on board the MMS satellites. He is the author of numerous refereed journal articles that tackle subjects like flux transfer, fast plasma, X points, and flux pileup. Stay tuned, there's some more fun words to say. Yes. Dr. Dorelli received his undergraduate degree in physics from Purdue University, and he received his PhD in physics from the University of Iowa. His postdoc years were spent at Los Alamos National Laboratory, and before joining Goddard, he was a member of the research faculty at the University of New Hampshire's Space Science Center. So today, Dr. Dorelli will take us on a fantastic voyage of mysterious magnetosphere, cosmic physics, microphysics, space plasma, and space weather. So please join me in welcoming Dr. John C. Dorelli to the Library of Congress.
Well, thank you so much for that introduction, and no worries, I have trouble pronouncing some of these things myself. And actually, there's a movement afoot on the MMS team to try to change the name of the mission. And I'll explain a little bit more about that. But it's really great to be here. Thank you all for coming. This is really a special treat for my wife, Roz, and me, because ever since we moved to the DC area 6 years ago, we've been wanting to visit this library, and just never had the time. So this is really a great honor to be here, and it's just a real treat. So what I'd like to do today is try to explain why NASA went through all the trouble to build these 4 big spacecraft and send them out into deep space. MMS stands for Magnetospheric Multiscale. And it was designed to measure a process called magnetic reconnection. And what I'm showing here, I don't have a laser pointer, unfortunately, but can everybody see this arrow that I'm moving around? Good. So what I'm showing here are 4 examples of magnetic reconnection that many of you may be more familiar with than the magnetosphere. On the upper left here is a classic Hubble image of the Crab Nebula. And here is an image of the sun showing a solar flare. And many of you may have seen photographs, certainly, of the Aurora, or maybe even in person. And then here is another great Hubble image on the lower left of another example of an Aurora, not on Earth. This is on Ganymede, which is Jupiter's 3rd moon, Galilean moon. And here we're getting a global picture of the Aurora, which people think is similar in many ways to Earth's aurora. So MMS is in many ways a culmination of many decades of space exploration. What we're showing on the left here is this classic photo op of Explorer 1, which was the first spacecraft that the US launched into orbit, and the first science mission, really the beginning of magnetospheric science. And this is James Van Allen in the center here. Oh, I lost my arrow. James Van Allen was responsible for the science instrument on Explorer, which is basically a Geiger counter. We've come a long way since then, but the big discovery of Explorer was the Van Allen radiation belts. And this really put the University of Iowa on the map, which is where I did my graduate work and got into space physics in the first place. But we've come a long way since then. Now, photo ops like this are no longer really possible. Because we cannot lift these big spacecraft over our heads. And we have really now fleets of spacecraft that have explored every corner of the magnetosphere now. And MMS is really the most complicated mission to date.
It does work.
Oh, it
the
works.
top one.
Oh, okay.
It should, the top.
Thank you so much. I now do have a laser pointer, theoretically.
Oh, it was working. Okay.
It's running out of batteries.
Okay.
So.
Never mind.
So the title here, I'm a really big fan of hard science fiction. And I was kind of inspired. I sometimes like to think of the magnetosphere as if it's a living organism. Plasmas sometimes have a life of their own. And if anyone has seen the 60s version of this movie, you realize it's not really hard science fiction. And, it's about shrink-raying a group of scientists into the human body so they can explore it on the cellular level. And Isaac Asimov actually, this book did not come before the movie, the screenplay. It was written before that. And Asimov kind of wrote the book under some protest. He thought, well, this is not physically possible to shrink people to the molecular level. But actually, in the magnetosphere, size is all relative. So in a sense, it is possible. I mean, our spacecraft on the scale of the magnetosphere are really like little nanobots exploring it from the inside out. It's exploring every little microscopic region of the magnetosphere. So I think a good place to start introducing reconnection is to go to the opposite end of the spatial scale and look at astrophysics examples. And on the left, again, this is the Hubble image that many of you have possibly seen of the Crab Nebula. And the reason astrophysicists are interested in reconnection in the context of the Crab Nebula is that a few years ago, the Fermi Space Telescope observed something really interesting in gamma rays. You get these giant flares, we're called super flares, in the Crab Nebula that kind of explode and brighten on timescales of days to weeks and produce enormous amounts of energy. And the estimate is that the particles are coming out at greater than 100 MeV. It's really hard with sort of classical astrophysics explanations for particle energization to explain those energies. And one of the processes that has been proposed is that magnetic reconnection may be responsible for this. Why are we as space scientists interested in this? Well, it really all starts with the sun, which we're particularly familiar with today on this very hot day. But it turns out that the sun is not just this uniform bright disk. It has interesting features on its surface. And Galileo, although he didn't discover sunspots, is most famously associated with them, observing them through his telescope. There's sort of a myth that he looked at the sun with his telescope and went blind doing this, and that is really just a myth. It's not a myth that you should never, ever do something like that, but he was a pretty clever guy, and he knew how to observe the sun. He put a screen behind his eyepiece and then just did some drawings of these sunspots as they were rotating around the sun. Here is another example of a rendition of the solar corona. The surface of the sun isn't really where all the action is happening. All of the stuff is happening really in the atmosphere of the sun, what we call the solar corona outside. And the corona is much hotter. And I may be sort of looking at this through parent goggles, definitely I am, but my 2-year-old last year drew this picture of the sun, and I claim that this scribble here is a coronal mass ejection. But certainly you can see magnetic field lines emanating away from the surface. To see these really in the corona, you have to block out the photosphere, the thing that Galileo was looking at. And then all of this interesting structure pops out. You can see these lines, these filaments, and some things that kind of look like loops, loop-like structure. These are the sun's magnetic field lines. And you can see them because the corona is so hot, it's about 1,000,000 degrees Kelvin. The surface, where you see the sunspots in the photosphere, is only about 5,000 degrees. So the corona really lights up the plasma that's trapped in these magnetic field lines. And so again, we've come a long way in 400 years since Galileo's telescope. We now have giant space telescopes orbiting everywhere. I said a little bit about Fermi observing the gamma ray flares. We have Hubble. We also have something called Solar Dynamics Observatory, which was launched in 2010, and whose purpose was to just continuously observe the sun in a wide range of wavelengths. And it's sitting at geosynchronous orbit, just constantly looking at the sun. And we've got a really much better view now, much higher resolution of the sun than we had in Galileo's time, that we've ever had, really. Here's a close-up view of sunspots, just to give you a sense of the scale. The reason these things appear dark, by the way, is they're not actually dark. They're actually very bright. If you put one of these next to the moon, it would be brighter than the full moon. But it's much colder than the surrounding photosphere. It's only 3,000 degrees as opposed to 5,000 degrees. So when you compare the two, this looks much darker. Here's an example of some of those, close-up view of some of those magnetic loops. We call them active regions on the sun. And these tend to be associated with the sunspots. The magnetic field lines originate in one spot, and then they loop around and terminate in another spot. And when you get all these complicated patterns of sunspots, you can imagine that the magnetic field topology can be very complicated. So here's a neat global image of the sun in UV by SDO for a whole month. You could just sit here and see the sun rotate completely around. And what I want to draw your attention to, so in UV, you're really seeing the corona now on the full disk. Whereas with blocking out the photosphere, you can only see the limb stuff. And so now you can see these loops on the limb, but as they rotate around, you can see the tops of the loops, and they tend to be bright, these active regions in UV. But you also see these dark regions. We call these coronal holes. And these are the places where that magnetic field, those field lines are open into interplanetary space instead of looping back around to the surface. And this is where the sun's atmosphere is blowing out to form the solar wind, this supersonic wind that's actually making it all the way to Earth. So if you're interested in staring at this for longer periods of time, you can just walk down the street and see this giant Ultra HD image rotating around at the Air and Space Museum. And I took my family and some friends to see this recently, and it really is kind of an amazing thing to look at. I mean, they didn't think it was real. It was like, well, that's just a simulation, right? That's not the real picture of the sun. This is a real picture of the sun. The picture doesn't really do it justice. It's really worth it to go there and take a look at it. So I think now you know everything you need to know to get a sense of what magnetic reconnection is. So in very simple terms, it's what happens when you have two magnets coming together and a plasma in between. And so if I have two bar magnets, I can just do this experiment on Earth, and they're oppositely oriented. The field lines will cancel in the middle, and I get what we refer to as an X-point magnetic field topology. The field actually vanishes at that point. And so I can imagine, just draw a little cartoon. What happens if two of these magnetic loops on the sun just come together and collide? Well, what happens is you form a little X point in the middle. And because, if I just took two magnets in this room and put them together, nothing really interesting is going to happen. I can move them around. It's just, nothing really interesting happens. As soon as I put a highly conducting plasma in there, these magnets don't like to come together, and they'll form really intense currents in the center near where this X line is. Basically, a giant electrical discharge is what happens. And this is not the most spectacular flare that has ever been caught by SDO, but it's really great because you can almost see these loops coming together and colliding. It's one of the few images of a solar flare where you can see reconnection actually happening. So can everybody see that? You can see one loop We'll wait for it to rewind. One loop here and one loop here, and they're kind of coming together, and then you see something move out this way. That is reconnection. So that still doesn't explain MMS, because we went from the Crab Nebula to the sun. What does this have to do with Earth's magnetosphere? Well, it turns out that these eruptive events on the sun actually have impact on the Earth. And one of the most familiar examples is the Aurora. Here's a great picture of the Aurora. The question is, what generates the Aurora? And what is the connection with the sun? So here's a great way to see this in action and on a global scale. On the left, you saw a solar flare eruption, or on the right rather, and on the left, what you're seeing is an image that was put together by NASA's Themis mission, has an array of cameras that extend from eastern Canada all the way to Alaska. They're just looking up at the sky, observing the aurora. And so you can see what we call these auroral substorms, auroral storms, developing on a global scale. And these things we know are associated with big eruptions on the sun. If we see something like a coronal mass ejection off the sun, we know that a couple days later, we might be in for some good auroral activity. So here's some data. It's nice to have a few examples, but we have years and years of data showing that the number of sunspots, is actually correlated with this AA index, which is basically a measure of how many storms we're having, magnetic storms, and you see there's a nice correlation here. So clearly the sun is having an influence on the Earth. So what powers the aurora? What is the physics? It's been a mystery for a long time, and this famous print illustrates, I think if nothing else, the state of scientific knowledge in the 16th century. We know a lot more now, though. The key, and it's been known for a long time, the Earth has an intrinsic magnetic field. You can think of it as a big bar magnet with a south pole and a north pole. And at Earth, the north pole is at the south geographic pole, and the south pole is at the north pole. So the magnetic field lines kind of come out and look like this. This is what we call a dipole pattern. We also know that the aurora, and we've known this also for a long time, the aurora, it tends to be organized around the poles in these ovals. And people have done statistics. Elias Loomis has this famous map where he looked at the statistics of aurora, how frequently do they happen at various latitudes. And you can see most of them happen in this band. We now have global images. This is from the Polar spacecraft in UV. So we have a good handle on the structure of the aurora and its time dependence, and its association with the magnetic field is pretty clear when you look at images like this. If you're interested, a colleague of mine at Goddard, Elizabeth McDonald, has a project called Aurorasaurus, where you can basically do what Elias Loomis did, track the aurora and keep track of where it is, but it's sort of a citizen science version of this. Anyone can just go to Twitter and say they see an aurora. I saw an aurora, and Aurorasaurus will track that and actually build up statistics of where the aurora happens. There's also a lot of great information about space physics in general and the aurora if you're interested. So one of the first explanations for the aurora was put forward by Christian Birkeland. And the idea is that his idea was that every now and then the sun, a blob of electrons will just explode from the sun. This was before anybody knew about coronal holes or the solar wind or anything like that. So this is really kind of an out there idea at the time. And these electrons travel from the sun to the Earth, and because of the Earth's magnetic field, it's like a cathode ray tube. They get guided by the magnetic field, and they tend to come in around the magnetic poles. And he actually did experiments called Dorelli experiments, little Earth experiments, just a magnetized sphere, and you shoot electrons at it, and you see that they tend to congregate in these polar regions. And so that was a very compelling explanation for the aurora at the time. People didn't like this idea, and this will be a running theme of the talk. Every time somebody has an idea that's really good, the scientific community kind of rebels against it and says, no, and in fairness, there are good reasons why this idea is not a good idea. The main one being the blob of electrons. So people objected, Lord Kelvin objected, you can't have a blob of electrons. I mean, they're all negatively charged, and we know from basic physics and chemistry, if you have like charges, they tend to repel. So how does this thing kind of maintain its coherence as a blob of electrons from all the way from the sun to the Earth? That was actually a real objection. And but you can see the experiment, it's very compelling, so it's interesting. How do we make this work? Well, the answer was not achieved until 1958, when Eugene Parker came up with his theory of the solar wind. And Parker, this was also not accepted at the time. Parker said, the corona is so hot, it should expand supersonically into space as a wind. And he had a nice mathematical model of this, but nobody believed him. There was actually a competing model called the solar breeze. But Parker had really good timing. It was 1958, and if you remember 1958, as I showed in the first slide, that was when we started putting stuff into space. And it wasn't long, it was a couple years later, where a spacecraft actually went out into the solar wind and saw the solar wind. And this is like a spectacular example. I mean, Parker was like instantly the most famous space scientist, astrophysicist in the space science community for predicting this. It's very rare that happens. You predict something so controversial, and then in your lifetime, 3 years later, somebody goes out and measures it, and you're... So it was kind of an amazing thing, but it solved the problem of how you could have particles coming from the sun and making it all the way to the Earth, because it wasn't just a blob of electrons. It was what we now call a plasma, which is a collection of electrons and protons. And one of the properties of a plasma is that it tends to be charge neutral. There are just as many protons as there are electrons, so it can maintain its coherence as it blows out into interplanetary space. So that solved the problem of how stuff from the sun can actually get to the Earth. And then a few years after that, James Dungy put it all together in one fell swoop. He said, oh, well, okay, we know there are these theories of solar flares, like I just showed you, that say, well, you have these two magnetic structures coming together, you form an X point, and you can release lots of energy. Well, if the sun is blowing out to Earth and it carries the coronal magnetic field with it, it collides with Earth's magnetic field, and you should have exactly the same thing happening. You have these two magnetized plasmas colliding with each other. And in this cartoon that he drew, which was in 1961, it was a 2-page paper. And he drew this little cartoon and basically solved the problem. You can see that the cartoon that MMS is using hasn't really changed all much from that, except we've added color to it, right? But it's basically the same cartoon. So what is really going on here? I'd also like to mention James Dungy passed away almost a month ago. And so I think it's appropriate to quote from the eulogy by David Southwood, which really brings home the significance of his work. Again, 2-page paper, basically solved everything. MMS, it's fair to say, would not exist without it. The whole theory of reconnection maybe would not exist, would not have been developed. But people didn't really accept this immediately. It took a long time for people to really come around to the idea that reconnection was happening in Earth's magnetosphere. And again, what happened is it was spacecraft observations. Our instrumentation got more sophisticated, and we were able to actually put spacecraft out to this region where the solar wind is meeting the magnetosphere and see reconnection happening. We didn't actually see into the X point, but we saw some of the consequences, the acceleration of the plasma that could only be coming from reconnection. And so that really started to turn things around. The best way to get a sense of what's going on is just to look at a movie. So here's a movie of basically what Dungy's idea was, of Dungy's cartoon. So the idea is that what happens is you either have the solar wind, high-speed solar wind stream, or a coronal mass ejection or something hitting the front side of the magnetosphere, which we call the magnetopause, and then the field lines kind of break and get transported around to this extended tail region, which is like a wake in the solar wind. And then those field lines come together, and there's a reconnection event. You have colliding magnetic flux tubes, and particles get accelerated, and behold the aurora. But there are other effects as well. It's not just the aurora. You're banging on the Earth's magnetic field. You're producing these magnetic storms in the tail. You're energizing particles. These things can actually have effects on society, right? I mean, they can have effects on our technology. because you might be inducing very large currents near the surface of the Earth, for example, if you distort the Earth's magnetic field like this. So this brings me to the next main topic, space weather. Why do we, it's an interesting physics problem, but why should we actually care about this? Why should the average person care about this? And again, I'm a big fan of hard science fiction. My favorite author, I would have to say, is Larry Niven. And one of my favorite stories of his was The Inconstant Moon. And this was about an amateur astronomer who was walking out one evening and noticed suddenly that the moon was brightening. It was starting to get really bright, almost so bright you couldn't look at it. And he turned this into a science problem. Okay, let me try to think of all the possible explanations of what could be going on here. And the first explanation was maybe it was the sun is going supernova, but probably not. It turned out that it was a giant solar flare coming from the sun. And what was going on was it superheated the atmosphere so that the other side of the Earth was in just total Armageddon and chaos. The oceans were boiling. Eventually it was going to come around to his side, and so they escaped to a tall building and just waited for the floods to come. Really, that is not what would happen if we had a big solar flare. We kind of know what would happen because these things have happened before, right? So there's this event, this famous event called the Carrington event. This was a very large, I think the biggest solar flare on record, the biggest CME on record that actually hit the Earth in 1859. And we weren't as dependent on technology at the time, but we did have things like telegraphs, and telegraph offices actually caught fire. Machines were sparking, desks were catching on fire. They all, globally just started misbehaving. And the Aurora was absolutely brilliant. It was amazing. You could see the Aurora all the way down to the Caribbean. People that were sort of camping in the Rockies were awakened and thought, oh, it's morning, let's start making breakfast. I mean, it was an amazing thing, but it wasn't a global catastrophe. The problem is that these things are very rare. They happen maybe every couple hundred years or something like that. They're so rare that we don't really know what their statistics are. And we've come a long way technologically since 1859. So there's a big question, if something like that happened, what would be the impact on today's technology upon which we're so dependent? So it's not an academic question because a CME as big as the Carrington event did happen recently. And this was July 23rd, 2012, and it missed us by about a week. If the sun had rotated another week, it would have hit us head on. And nobody knows really what would have happened. But one of the impacts that's been estimated is that, well, what if it knocked out the power grid globally? And we had to order new big transformers, and how long would that take? We don't do very well, particularly in weather like this with no power for a week. Imagine not having power, everybody not having power for a year. Now, admittedly, this is maybe very pessimistic thinking, but the point is we don't know how to model these things. We've never seen another event like this. We've come a long way since 1859. We just don't know what would happen. So it is something that we should keep our eyes on. But there are a lot of other effects, space weather effects, that are kind of under our radar, under the radar of the general public. You could call them hidden space weather effects. You can get damage to spacecraft because things like solar energetic particles are emitted when you have a big solar flare. You can have GPS effects. I mean, we're all very dependent on GPS now. I mean, these big events can cause irregularities in the ionosphere that can affect GPS timing. If we really, being the science fiction fan that I am, we need to get out into space and start exploring. If we really want to sort of be a spacefaring race and explore other worlds in our solar system, it would be good to be able to predict the weather in space for various reasons. So there are good practical reasons for being involved in this that don't involve being interested in this that don't involve Armageddon. The big problem is that we're really behind, regular weather modeling. I would say we're a few decades behind there in our ability to simulate these things. With regular weather on Earth, we know what the physics equations are. We have a good handle on all the physics. It's just a question of getting bigger machines and being able to do predictions more in advance and that sort of thing. With space weather, our models are really limited by the physics. We don't actually have a good idea of what the right physics equations are. Plasmas are a lot more difficult to model than the air in this room, for example. But we try, and we use models. I just found out before the talk that at least one person in the audience did their PhD thesis, did their thesis work on magnetohydrodynamics. That's probably the only person, I would guess. But those are that is the math model that we use to simulate these things now. And it's a very limited model. And the reason it's very limited is that it excludes the very region where magnetic reconnection is happening and where MHD breaks down. So this model is breaking down in the very region that we need to understand in order to have a predictively powerful model. And that's really the big motivation for MMS. MMS was designed not to immediately solve all our space weather prediction problems, but to really understand the physics of this process. Its orbit was designed so that it would maximize the probability of flying through these regions where we actually think reconnection is happening. There's one on the day side here where the solar wind is coming in and hitting, and then there's another one on the night side in the tail. And the orbit is designed to cut through these regions and make what you could call very high-speed photographs of what's happening as these magnetic explosions are occurring. And previous spacecraft couldn't do that because the time resolution wasn't good enough. Typically on a previous mission, like the Themis one that I showed earlier, it takes, you put one particle detector on the spacecraft and it spins around, and it typically takes a few seconds for the thing to spin around. So you have to wait that long before you get a picture of the whole sky. With MMS, we've got 32 instruments arranged all around the spacecraft, so we don't have to wait for the spacecraft to spin around before we get a picture of the sky. And we've increased our time resolution here by about a factor of 100. This is going to allow us to actually see this process in action. And the reason we have 4 of these spacecraft is because we want to be able to measure how things vary in 3-dimensional space. It's not enough just to get the time resolution. We want to get the spatial structure too. It's a very, like I said, a microscopic region on the magnetosphere that we're trying to cover. So there are a lot of instruments, as you might imagine, if you're trying to capture a very complicated plasma physics event like this. You need lots of antennae and particle detectors, and there are 20 plus instruments on each of these 4 spacecraft. They have to be big spacecraft. Each one of these things is about 2,500 pounds, about the size of my Honda Civic, and they're all stacked up into the fairing of this big rocket. I mentioned before that, so the instrument that I'm involved in is called the Fast Plasma Investigation. And this is, I would argue, the most important instrument on the mission, not only because I'm involved in it, but because it's the one that's going to be doing the high-speed photography of the particles. It's really the kind of the big new thing on MMS. And so we have 16 particle detectors measuring electrons, 16 measuring ions on each of the 4 spacecraft. Here's the team, our intrepid principal investigator of FPI, Craig Pollock, and the team of lab people calibrating the instrument. This has been, if you can believe it, almost a decade, maybe even more than a decade of effort since the planning of the mission and the development and the testing of all the components up until launch. I only became involved in this about 6 years ago when we moved to, when I moved to take a job at NASA Goddard. And it's been an amazing ride, really. That's all I can say about it. And it's involved in many other institutions as well, just for this instrument. MMS launched in March, and this was the first launch that I ever got to attend. I had never actually even been to Kennedy Space Center until then. And it was really just an amazing experience. Here are the 4 spacecraft stacked up. This is see this little thing up here? That's the rocket fairing, right? And so this is a big Atlas V rocket. One of the things I really loved about visiting the Kennedy Space Center was to just get a sense of what NASA is still doing. You don't really kind of see a lot of this anymore all the time. I mean, they're always launching these things, these big missions. We hear a lot about SpaceX, and I love SpaceX. I love what they're doing. But it's good to know that NASA's still doing this sort of thing, too, on a regular basis. There have been some 54 Atlas V launches. There was one partial failure in all of those. So they have a pretty good track record of doing this kind of thing. It launched on March 13th. And here's a video of the launch. This video was taken by my wife, Roz, while we were in the bleachers. It's not the most impressive close-up NASA video of the launch, but I think it captures the mood in the bleachers, which I thought was... And the video doesn't really do it justice. It's really an amazing thing to actually see. I think that high-pitched screaming in the background might be me. I know it's not my 3-year-old daughter because she fell asleep 15 minutes before the launch. And it went off without a hitch. Everything just went perfectly. It was just an amazing thing after people have been waiting for so long and worrying about everything. Here's a much quieter video from the Centaur. You'll actually see one of the MMS spacecraft separating from the Centaur. There it goes. And pretty soon you'll see one of our instruments rotating into view. There's one of our instruments. They're arranged all over the side of the... we're not getting science data yet. We're in commissioning mode, and we'll be in commissioning mode. Commissioning activities, the commissioning phase is where all the instruments are slowly turning on and everybody's making sure it works properly. The testing, calibration, making sure we don't interfere with each other. There have been, many glitches, but nothing that, it's been amazing to see the commissioning team coming together to solve all the problems as they arise. And it's going to be a long wait for the data. We're expecting to get our first data, real science data, in September. So stay tuned for that. And that's really all I have. We have plenty of time for questions, so I hope you come prepared with questions. Thank you.
And if you could repeat the question, you could paraphrase it or whatever
Okay.
for the capturing. Questions? Oh, yeah.
So you said the solar winds, like the emissions, they come obviously from the sun. And do they just come from the reconnection of the fields, or do they are constantly being emitted?
Yeah, so the question is, the solar wind, is it really driven by reconnection, or is it something that's just a constant property of the sun? And the answer is it's something that's just happening continuously. So the way you think about this is, remember in that big SDO image I showed, these dark patches? The solar wind is coming from those. It's just the corona, the atmosphere is so hot, its pressure is so great, it wants to expand out into interplanetary space because it's basically a vacuum it's expanding into. So whenever the magnetic field is open to interplanetary space, the corona will just expand out supersonically. The reconnection is something that happens on top of that continuous process, right? So you get one of these explosions, and then you'll get a blob of plasma that hitches a ride on the solar wind, so to speak, and flows out to Earth that way. So both of these things are happening. One of them is continuous, and one of them is a more sporadic process.
Curious, obviously we're working from a point to expansion from the perspective of the title of this topic as it's shown on the Library of Congress website. It may not have anything to do with that, but it talks about the universe.
Mm-hmm.
And maybe you could expand on what we're talking about from the perspective of our solar system and the universe, our sun, as a comparison to other things that we're trying to do.
Oh, sure, yeah. So the one example I showed of the universe was the Crab Nebula. And so at the center of the Crab Nebula, you have a neutron star, and it also has a magnetic field. and it's rotating around really fast. And the thinking is that energy is being converted from that magnetic field into particle energy through a reconnection process. So that's sort of the connection with what's going on the sun. The sun has a magnetic field as well. All stars have some level of magnetic activity, some more than others. And so people that study a relatively new area of research now is NASA's really into looking for habitable exoplanets. And one of the things you have to worry about is, well, some of these exoplanets are in pretty extreme environments. I mean, where you're getting these Carrington level flares, not every couple hundred years, but maybe a couple times a day, right? I mean, they're much more frequent. And so we are trying to model that process to understand what the impact on habitability is. So reconnection is playing an important role there. Anywhere there's a star, you're going to have a similar kind of solar wind, stellar wind planet interaction if the planet has a magnetic field.
Mars had a magnetic field is theorized. Do you have any speculation on why?
Well, Mars, this is another interesting question. Mars also has an aurora. It still has a magnetic field. It's called a crustal magnetic field. It's sort of a remnant magnetic field. So it has little loops of magnetic field lines on its surface in places, just like the sun does. And the solar wind actually will interact with those little pockets of magnetic field and energize particles, and they'll accelerate to the surface. And this has actually been with Mars Express mission, for example, has observed aurora on Mars. So it really is a universal process. Anywhere you have plasma and magnetic fields, which is pretty much everywhere in the universe, this process can happen.
Do the scientists have a sense of what percent of the exoplanets are being hit with Carrington?
They do actually. I just saw a talk on this a couple days ago, and I can't quote the number. I don't remember what it is. But people are actually looking at that now. What percentage of stars have magnetic activity on the level of a Carrington event, and what's the frequency, and even what you can look at subsets of sun-like stars and see how often these events are happening because you have lots of time history, right? And get a sense of the statistics of these Carrington level superflares from looking at other stars.
You don't know the exact number. I mean, was it more than 50% or less?
No, the number that I heard was something like one of these Carrington level superflares every several hundred years. And there's a whole range. You can get flares that are much larger than the Carrington event, and they will happen every, say, 5,000 years. It's a lot like asteroid impacts. That's how you would think of it. There's a distribution of these, and the biggest ones are less frequent than the little ones. Yep.
When you say reconnection event, I thought magnetic fields were continuous. What's disconnected?
Yeah, so the terminology, we get that question a lot from people that understand electrodynamics, right? And it's just a little bit of unfortunate terminology. Dungy was the one who actually coined the term reconnection. And the reason we do that is because in the MHD approximation, in this fluid approximation that we use to model these things, the plasma likes to stick to the field lines. And if the plasma sticks to the field lines, it can never mix into, you can never get, for example, something like a solar wind plasma mixing with the Earth's magnetosphere because the two fields don't mix. With a reconnection, what happens is, yes, the field is continuous, but there are places at these X points where the field might vanish. And when the field vanishes, MHD breaks down. Your fluid model is actually breaking down and allowing the plasma to mix. And so stuff that was on one field line could get onto another field line. And this is what we mean by reconnection. It's not that the field itself is actually breaking and reconnecting and changing its topology. It's that plasma is getting mixed up. So it's just terminology. It is confusing terminology to people outside space physics, I admit.
What's creating the great energy at that point?
So the way you want to think about it is you have these two regions of magnetic fields with different plasmas in them. And the magnetic field carries an enormous amount of energy. And when you put two regions of magnetic field together that don't want to be together, you can, in a very thin region in between the two magnetic regions, you can actually convert some of that magnetic energy into plasma energy. One way to think about it is if you have two balloons that are coming together and they don't want to be together, but you keep pushing them together, and then suddenly something explodes and you release energy, you release tension or whatever. It's that kind of thing that's happening.
So, how active is our sun in comparison to like the other stars in the universe, as far as like solar activity with the flares?
Yeah, that kind of goes back to the question of the statistics of solar activity, and I couldn't tell you, I couldn't give you a good number on that right now. You'd have to ask some of my astrophysics colleagues who study these statistics. But there are significant numbers of stars out there that have much more activity than the sun, that are, like I said, are producing these Carrington level events much more frequently than at Earth. Yeah, that's all I can say about that. I don't have the exact number for you.
Is
Yeah.
there something that makes our sun inherently different so that it doesn't have these large Carrington levels?
No, it's just statistics.
We're just lucky.
Yeah, we're just lucky. That's it. And actually, we're more lucky than that. Early, there's, for an individual star, stars have life cycles, and the sun, early in its history, was thought to be much more active than it is today. You might have been having these Carrington level events every week or something like that, right? In the sun's early history. And so people look at the implications of that for the development of life on Earth. It's one of the factors that might have affected the development of life on Earth.
I've always been curious as to what happens when the north and south pole of the sun and what impact that will have.
Not very much impact, I think. So if you think about it, this sort of thing happens in the solar wind. The solar wind can sometimes be northward and southward, and there's not much impact. I mean, you might ask the question, what happens if the magnetic field suddenly went away? And if it went away for a long period of time, then we have examples of what the solar wind planet interaction is without a magnetic field. And in that situation, what happens is, so in the upper layers of Earth's atmosphere, we have an ionosphere, which is a partially ionized plasma in the upper layers of the atmosphere, and it conducts currents. And when the solar wind hits that ionosphere at a planet that's unmagnetized, like Mars or Venus, for example, you induce currents in the ionosphere, and it kind of shields you from the solar wind. So the ionosphere itself will, to some extent, shield from the solar wind. But it's a very good question. I mean, we don't know, exactly what the impact on life and society would be if something like that happened. In fact, it's something that people who are studying habitability are interested in. And we compare Venus with Earth to understand what the effect of the magnetic field might be on the solar wind planet interaction. So just the reversal itself, not a big deal. If the reversal were accompanied by the magnetic field going away, things might get interesting. Yeah.
Let me understand the orbital profile of these four modules. I mean, they must be very elliptical if you're covering
They are, yeah. So, good question. The orbits were designed, so the mission is designed in 2 phases. And in the first phase, we're trying to go after one of the X points on one side of the magnetosphere. And so we have a very elliptical orbit that's going all the way out to like 76,000 kilometers above the surface to hit that X point. And then the orbit actually precesses around the Earth. And so there's another phase that's going to happen about a year later where we're going to be exploring the other side in this highly elliptical orbit. So it was designed that way on purpose to get us out to where the reconnection is happening.
And the relative position of the four modules, or how far away from
Yeah, that's another new thing. Let me repeat the question since I've not been doing that. The question was, how far apart are the spacecraft going to be? That's another very new thing about MMS is we've had constellations before with like the cluster mission and Themis, but they've never been this close together, and they're going to be about between 10 and 100 kilometers apart. And they have to be so close together so that they can, because this region that we're trying to cover is that small. and we'd like to be able to resolve the three-dimensional structure of it. Yeah.
What's the difference between the solar wind and a coronal mass ejection, for example, in terms of its composition?
Oh, another good question, right? So there are differences between in the parameters of the plasma between coronal mass ejections and in the solar wind because of their different origins, right? So the solar wind is coming from these dark regions that you saw in the UV, these coronal holes, and they tend to be hotter and less dense, if I'm remembering correctly. And the stuff that's confined in these coronal loops tends to be more dense, and you can think of it as sort of a pressure cooker. This plasma is kind of trapped in there for long periods of time. So yeah, they're very different types of plasma that you see in CMEs versus just the steady solar wind, just because of where they come from on the sun.
Can I ask a quick question?
Sure.
I recently saw some articles in semi-popular press about, I think it was a grad student in Australia that said that she discovered there were plasma tubes on Earth. Is that something that MMS is going to confirm or deny?
I have not heard. There's so many like terms in magnetospheric nomenclature, but I haven't heard of that one. Plasma tubes. I mean, there's certainly, there are lots of different populations of plasma in the near-Earth space environment that can get onto these closed field lines at Earth, right? There's a population called the plasmasphere that's close to Earth, and it can fill magnetic flux tubes close to the Earth. Stuff can come in from the solar wind and get onto these closed field lines. So you have lots of different populations of plasma that can get onto the Earth's magnetic field lines. But I hadn't heard of that specific thing.
MMS is not looking at those.
No, MMS is not designed to look at stuff that's happening close to Earth, like in the plasmasphere, for example. It's really looking at the place where the solar wind is meeting Earth's magnetosphere, much farther out.
Okay. Well, thank you. I guess we're done.
This has been a presentation of the Library of Congress. Visit us at loc.gov.